All right, so we are given the instructions. I find the domain of the given function, then find the x-intercept and the vertical asymptote of its graph. Okay. So this is the transformation of the logarithmic function in base 4, and 4 is greater than 1. So just for kicks and giggles, let's draw the basic log function in base 4. Right? We know it's going to look like this. Across the x-axis at x equals 1. Okay. The y-axis is the vertical asymptote, and it goes up and to the right forever. And so this is the graph of y equals log base 4 of x. Okay. And f of x here is the transformation on that function. Okay. So you know when you replace x with x minus 4, that's going to shift the graph to the right 4 units. And then when you multiply the log by 2, that's going to do a vertical stretch by a factor of 2. And then when you multiply it by minus 1, okay, it's going to flip the graph over the x-axis. And then lastly, when you add 1 to the right-hand side, it shifts the graph up 1. Right? So there's actually 1, 2, 3, 4 transformations on this basic log function, right? Log base 4 of x. Okay. So f of x is equal to 1 minus 2 times log base 4 of x minus 4. All right. So remember the input to the log function we call the argument. And for our basic log function over here, log base 4 of x, we know the domain is x has to be greater than 0, right? You can't take the log of 0 and you can't take the log of a negative number, right? It's undefined. So x has been replaced with x minus 4. So to find the domain, we just set the argument x minus 4 greater than 0. Over here, the argument x greater than 0. Okay. And when you solve for x, you get x has to be greater than 4. And so the domain is all real numbers greater than 4. So in interval notation, we write that parenthesis, 4, comma, infinity, parenthesis. The x-intercept is where the graph of this function crosses the x-axis. So you know to find the x-intercept, you set y equal to 0. Solve for x, right? So because x is replaced with x minus 4, right, we know that shifts the graph to the right 4 units. And you might think the x-intercept set x equals 5. But because of the vertical shift, okay, and the stretch and the flipping over the x-axis, right, it's the x-intercept's not at x equals 5, it's somewhere else. Okay. So we got to find it. So we replace, remember, function values and y values are the same. So we replace f of x with 0. And we have 0 is equal to 1 minus 2 times log base 4 of x minus 4. And now we got to solve for x, okay? So, got to isolate x on the left-hand side. So this product here right, minus 2 times log base 4 of x minus 4, right? I can move it to the right-hand side, or left-hand side, excuse me, by addition. And I have 2 times log base 4 of x minus 4 is equal to 1. All I did was move minus 2 times the log of x minus 4 to the right by addition. And now you can see on the left, this is a product, right? This is 2 times log base 4. So I can divide both sides by 2 and isolate the log on the left-hand side. So we have 2 times log base 4, x minus 4 is equal to 1. We divide the left side by 2, we divide the right side by 2. And so the 2's cancel on the left, and we're left with log base 4 of x minus 4 is equal to 1/2. Now I want to remind you of something from page 1 of this lecture handout, lecture guide. Okay. Y equals log base a of x, and x equals a to the y are equivalent equations, right? And so on page 1, right, we did some exercises where we converted logarithmic statement to an exponential statement, and an exponential statement to a logarithmic statement, right? Well, in this case, the base a is equal to 4, and the exponent y is 1/2. What's different is the input x has been changed to x minus 4. So if we have x minus 4 here, we have x minus 4 here in the exponential. So if we write the equivalent exponential statement, we have the argument or input x minus 4 is equal to the base a 4 raised to the y power 1/2. Right. So remember, in this case, a is equal to 4, the base a is equal to 4, and the exponent y is equal to 1/2. Okay. What's different is instead of just x on the left-hand side, we have x minus 4 on the left-hand side. Okay. Well, you know, anything raised to the 1/2 power means square root. So we have square root of 4 on the right, and square root of 4 is 2. And when we add 4 to both sides, we get x equals 6 is the x-intercept, or the point 6, 0. Any questions on that, ladies and gentlemen? All right, so the last thing we have to find for this problem is the vertical asymptote. And you notice that over here, the vertical asymptote is the vertical line x equals 0, right? That coincides with the y-axis. So all you had to do, and technically all you did, was you take the argument x and you set it equal to 0. Okay. So over here, the argument is x minus 4. So to find the vertical asymptote, we set the argument x minus 4 equal to 0. And we solve for x. So x equals 4 is the vertical asymptote. And this reminder cells, vertical asymptotes are vertical lines. So x equals 4 is the equation of a vertical line. Okay. And so when we replace x with x minus 4, that shifted the vertical asymptote 4 units to the right. And so it went from x equals 0 to x equals 4. Okay. Any questions on that, ladies and gentlemen? Okay. All right, let's take a look at the last one. I think I did correct this in Oaks. I had a couple of typos with this lecture guide. Okay. We're going to just find the domain. Of the function f of x is equal to the natural log of x squared minus 1. Again, right, this is the argument going into the natural log function. And so to find the domain, we set the argument or the input to greater than 0, and we solve for x. Well, this is an inequality, and it's a quadratic inequality, right? Because it's quadratic on the left. And we learned how to solve those when? Section 1.1. First week of classes back in January. Yeah. Math is cumulative, right? We don't forget what we learned in January. We bring it with us to April. Okay. So steps for solving a quadratic inequality: make sure 0 is on one side of the inequality symbol, which we have. Okay. Second step is to factor the quadratic. So x squared, well, we set the quadratic equal to 0, and then we factor it. And it's with these values of x that we divide the real number line up into intervals. And so we have x minus 1 is equal to 0. X plus 1 is equal to 0. X is equal to 1. X is equal to minus 1. So here's our real number line. Not very well drawn. Applies to the variable x. And so here's minus 1 on the real number line. There's plus 1. And if the numbers in this first interval, if one number in this first interval satisfies this quadratic inequality, all the numbers do. Okay? If one number doesn't, then none of the numbers satisfy the inequality. Okay? So that's why we use the test point method. Okay? Now, minus 1 and plus 1 make the left-hand side equal to 0. And 0 can't be greater than itself. So we put open circles on minus 1 and 1 to indicate they're not in our solution set. So for each of these intervals, we need a test point and then the value of the quadratic. Yes, ma'am.
How do we know that they're not in our test point?
How do we know what?
That they're not in our test point, negative 1 and 1.
They're not in our solution set.
So what is? Or are we finding them?
That's what we're finding there. That's why we gotta use test point method.
But we know that they're not in our solution set because we got them.
Because you put 1 in for x. 1 squared minus 1 is 0.
Yes.
And 0 can't be greater than itself. Okay, yeah. All right. So in this first interval, -2 is less than -1. And so when I put -2 in for x in the quadratic, I get 3, right? The value of the quadratic is 3, and 3 is greater than 0. So all these numbers, any real number less than -1, makes the left-hand side here greater than 0. In the second interval, it contains the number 0. And the value of the quadratic is equal to -1. So we put 0 for x to get -1. Well, -1 isn't greater than 0. So none of these numbers work between -1 and 1. And then for x greater than 1, I use 2 as my test point. 2 squared minus 1 is equal to 3. That's a positive number, right? And 3 is greater than 0. So any number greater than 1 makes the left x squared minus 1 greater than 0. Okay. Remember, you can take the log of a positive number. You can't take the log of 0 or a negative number. Okay. So if x is less than -1 or greater than 1, then our function is defined. If x is between -1 and +1, our function's undefined. Okay. So the domain in interval notation, -infinity to -1, union 1 to infinity. So you define the domain of a logarithmic function like this. You set the argument greater than 0 and solve for x. Set the input greater than 0 and solve for x. Okay. Any questions on that, ladies and gentlemen? Okay. So that wraps up 5.2. So now you have everything you need to successfully complete the web assigned homework. You win tomorrow night, right?